So we're going to start out discussing area today, of all things. And you've computed area, I'm sure, in geometry, areas of circles and triangles and rectangles. We're going to use some of that, but we're going to find how to find areas of regions bounded by arbitrary curves. Arbitrary curves generated by our functions that we're familiar with, polynomial, exponential, logarithmic, trigonometric, and so on. So that's our goal. And this is the main problem, really, that we tackle in Calculus 2. So first of all, we'll just start with simple understanding from a example that illustrates why computing area is important. So an object traveling in a straight line at constant velocity, then the distance traveled is equal to its velocity times the elapsed time. Some of you remember distance equals rate times time, right? Distance equals rate times time. And you know, we're going to be careful about units here. So look at this example. How far will an object travel if it moves in a straight line at 30 feet per second for 2 minutes? So this is clearly the velocity, 30 feet per second. We'll use v for velocity, or the rate. And the elapsed time is 2 minutes, so we'll use t. So we'll use v for velocity, and we'll use t for time. And then we have our distance traveled. We'll just call that d. So how far will the object travel? What will its distance be? It's the velocity times the time. And so you've got 30 feet per second is the velocity, and then times the time. But here we've got to be careful about the units, right? Because 2 minutes, are we going to multiply it by 2? No, because the units for our velocity are 30 feet per what? Second. Time units are seconds. So the easiest thing to do is to convert that to seconds, which of course is going to be what? 120 seconds. And the units even help us out. Some of you are familiar with units if you've had chemistry or physics. Feet per second, feet divided by second, times seconds gives me feet. Okay, so 30 times 120 is 3,600 feet. Okay, so that's make sure you're consistent there. I could have also converted my velocity from to feet per minute as well, but and then got the same result. But here's what I want to look at now graphically. I want to take a look at the graph of the elapsed time. This is going to be the horizontal axis. This is the elapsed time, t, and we'll do that now in seconds. Those are the units we'll use, so we converted the 2 minutes to 120 seconds. And then the vertical axis is going to be the velocity, which is given in feet per second. And if I were to graph the velocity as a function of time in this case, since the object's traveling at 30 feet per second at a constant rate, here's the graph. It's just a horizontal line, right? Here it is. And indeed, here's where area comes in. When you talk about multiplying 30 times 120, what's the geometric interpretation here? Well, for 120 seconds here, right, if I look at the area under this curve, if you want to think about it as horizontal line, it's the graph of a horizontal line, but the area under this line, of course, we get this rectangular area. And what's the area of any rectangle? It's the base times height, length times width, which is going to give me what? 30 times 120. It's giving me the 3,600 feet. And so the idea here that I'm trying to show you is, in this example, we can think of this problem of finding the distance of the object in terms of finding the area under the velocity curve. And this is going to be the way we're going to proceed. Now, what if the velocity changes? Okay, this is a constant velocity of 30 feet per second. Well, what if we have a car that's traveling at different speeds? Maybe the first 2 hours it's traveling at 40 miles per hour. From 2 to 3 hours it's in a lot of traffic or something and travels 20 miles per hour. From 3 to 6 hours speeds up to 50 miles an hour. And from 6 to 8 hours it gets 60 miles per hour. So if you go through different speed zones and stuff, that could happen, for instance. So we're just generalizing this problem to show you how we would illustrate this graphically. So first of all, how would I find the distance just straight up, right? Well, it's rate times time, and I would have to find the distance traveled for each of these 4 time segments. For the first 2 hours, it's 40 miles per hour times how many hours? 2 hours, from 0 to 2 hours. And then I add this 20 miles per hour. From 2 to 3 hours, that's just 1 hour. 50 miles per hour times the elapsed time from 3 to 6 hours, that's going to be 3 hours. And then 60 miles per hour, 6 to 8 hours is 2 hours, right? So this multiplies out to what I've got, 80 plus 20 plus 150 plus 120, and I get a total of 370. Of course, my units are going to be in what? Miles, right? Since each time I'm multiplying miles per hour times hour. So obviously that's the calculation, easy enough. There would be our estimate for the distance traveled. But graphically, we can also think about this, right? For the first 2 hours, if this axis down here is the time in hours this time, and this axis here now again is our velocity, this time in miles per hour, then what do we have? From the first 0 to 2 hours, we're traveling 40 miles per hour, so it's a constant rate over that interval. And then from 2 to 3 hours, we're at 20 miles per hour. And then from 3 to 6 hours, we're at 50 miles per hour. So here's 40, 60, 50 is halfway between. And then from 6 to 8 hours, we're going 60 miles per hour. And so here's what the graph of the velocity function looks like. Well, now to find the distance traveled, all we're doing is what now? Finding the areas under each of these curves, which constitutes finding the area under 4 rectangular regions. And so this first region, of course, is going to be what? The 80, right? The 40 times 2 gives me the 80 miles traveled there. Multiplying this, 1 times 20 is 20. This is what? 3 times 50 is 150. And 2 times 60 is 120. And of course, adding these up is the equivalent of what we did up there. So again, here's the picture that we have. And this is why the area problem is important. There's lots of problems where we need to, for instance, find the distance traveled, as this example illustrates. And there's other times we're trying to look at a net change in a quantity, or the accumulated value. And it basically boils down to finding the area under a curve. Now, in general, driving a car, we're not going to have this sort of choppy motion, right? The speed will change, as we drive. We might be, speeding up and slowing down, and so on, changing our speed. So the graph is going to look not linear necessarily. So what do we do with those? So let's look at the real problem that we encounter. Here's our problem. Consider this function, the function 1 over x, over the interval from 1 to 5. What is the area under this section of the curve? So maybe this is the velocity of your object over time, and your velocity is decreasing, right? It's not constant, it's decreasing. So what would be the distance traveled in that case, for instance? And we're going to just do this from x equal 1 to 5. So basically, I'm talking about the area under this curve. Now, this area under this curve is not a rectangular region, right? It's not a triangle, circle, or anything normal. How do we do that? I mean, we could sit there and estimate. I mean, we can estimate and see, clearly, if I look at this whole rectangular region here, which is 1 unit high, and what, from 5 to 1, or 1 to 5, 4 units, it's 4 square units, right? And the region we're looking for, which is, I'll shade that in, clearly going to be less than half that probably, right? I mean, you might estimate it's a little under 2 square units for the shaded in area. But what we're going to do is show you how we use calculus to find these areas. So one way to estimate the area under the curve is to break up the interval into strips, right? These strips are what we call a partition. It's the mathematical word for it. And the strips are subintervals. And then we try to approximate the area of each of the resulting strips. So for instance, we can use rectangles to approximate each strip. So here's the idea. Suppose I do strips of equal widths of 1 unit each. Right? In this case, going from 1 to 5, that'll give me what, 1, 2, 3, 4 strips or subintervals. Now, how do we draw each rectangle that approximates the area? So going from 1 to 2, I'm going to try and approximate this area here with a rectangle. Obviously, it's not going to be the exact area. Okay. Well, one way we can do it is we can determine the height of the rectangle by the function using the value of the function at the right endpoints of each interval, or each subinterval. So the first strip or subinterval from 1 to 2, if I use the right endpoint of 2, what's f of 2? If I just plug it into the function, I get 1/2, right? F of 2 is 1/2. And then for the next interval, I'll use the right endpoint, which will be 3. F of 3 is 1/3. And then from 3 to 4, I'll use the right endpoint 4, 1/4, and so on. So what would the rectangles look like in this case? So here's what they would look like. Okay, so here you have the curve, and the heights of my rectangles, right, for each subinterval are determined by this right endpoint. So I have 4 strips, 4 rectangles, and here's the area of the first one, or here's the first rectangle, here's the second, third. Looking at this, we could calculate the area. Let me get some water here, my voice is losing. Okay, so what I'm going to do is I'm going to designate this particular approximation for the area under the curve, which it's not exactly the area under the curve. I'm going to designate it capital R with a subscript 4. R is for right endpoints, which is what we use to determine the heights of these rectangles, and 4 for the number of strips or number of rectangles, 4 of them. Okay, so the first rectangle, what's its area? The base is 1, right? In each of these rectangles, the base is 1. But the height was what? The value of the function at 2, which is 1/2, right? So 1 times 1/2. Then 1 times what? The height of this one is what? 1/3. And then 1 times the height of this one, 1 times 1/4, 1 times 1/5. So I do the mathematics, I get this fraction, or about 1.283. Okay. Notice that this represents an underestimate, we would say, of the true area. It's clearly below the area because we're missing, right, this little part up here, this little part up here, that little part, and just that little sliver there. So we're missing a little bit of the area, right? So it's a lower estimate, if you will. Okay. So, well, we could also have estimated with rectangles, instead of using the right endpoints, we could have used the left endpoints of each subinterval. What would that look like? Well, it would look something like this. If we use the left endpoints now from 1 to 2, I use the value of the function at 1, which would be equal to 1. The height would be 1, right? And there's my rectangle. From 2 to 3, I use the left endpoint 2, so the height is 1/2. From 3 to 4, I use f of 3, which is 1/3, and so on. So I get these 4 rectangles, and I'm going to designate this as L4, L for left endpoints and 4 for the number of strips. So if I calculate the area of these 4 rectangles, I get them to be about 2.083. And notice this is an overestimate now, because we're a little bit over. These regions here, right, above this curve, areas of the rectangle above the curve, are not part of the area under the curve, right? But here's the thing then. What we've done is we've at least now sort of trapped the area under the curve between these two values, right? The lower estimate with the right-hand sum and the upper estimate with the left-hand sum. So our area is between here and here. Okay. So this is a way we're going to do some estimates, and we'll talk about how we can get a better estimate than this in the next video. But first of all, another method for finding subintervals, the heights of the rectangles, could be we use the midpoint. So the book will talk about the midpoint approximation, and that will be denoted M for midpoint as opposed to L or R. And then the N, the little subscript, would be, like the 4, how many strips you have. So like if I use, in this case, the midpoint would be what, from 1 to 2, be 1.5. And I would use the height there. If I come up here, look at that height, and then come across here, that would be the height of my rectangle for the midpoint. All right, and then from 2 to 3 would be 2.5, and that would be my height there. Okay. So those are what we're going to start with: left hand, right hand, and midpoint approximations is what we'll call those. So in the next video, we will take a look at some examples of that.